Hello, everyone. My name is Dr. Christopher Moore, and I'm a research associate at West Virginia University, and I lead the day-to-day operations of our grant-funded pollution prevention team. Our team provides no-cost pollution prevention assessments and other related technical support to businesses within West Virginia. Today's webinar is the first in a series of webinars focused on improving energy efficiency of industrial systems. The focus today will be on boiler systems. So before we dive in, let's quickly go over what this session will cover. We'll start with some background on industrial systems. Next, we'll briefly discuss the function and key components of boiler systems. After that, we'll look at how boilers work and some of the different types of boilers. And from there, we'll spend the rest of the session exploring the topic of boiler efficiency. We'll talk about factors that influence boiler efficiency and losses, then discuss some best practices for improving boiler efficiency. So before we jump into the discussion of boilers, let's look at what we mean when we talk about industrial systems. Industrial systems are the backbone of industrial facilities. These are the common systems that you'll find in almost every industry and are the primary targets when we evaluate and try to improve the energy efficiency of an industrial facility. These systems include lighting. We're all familiar with this one. This is the system that provides visibility in the facility. This includes not only the lamps and fixtures, but lighting controls, including ballasts, occupancy sensors, motion sensors, and timers. We also have HVAC, heating, ventilation, and air conditioning. HVAC systems control the climate and air quality in the facility. HVAC systems are essential for maintaining comfortable and safe working environments. And boilers are used to generate heat for comfort or to be used directly or indirectly in industrial processes. Motors are the workhorses of industry. They drive a wide range of equipment and processes. While small facilities may only contain a few motors, larger facilities can contain hundreds, if not thousands, of motors. Fans used in ventilation, cooling, and various industrial processes. Fans are used to manage airflow. Compressed air. Compressed air is a common utility in many industries, used for powering tools, equipment, and processes. And building envelope. The building envelope refers to the physical barrier between the interior and the exterior of a facility. That includes the walls, windows, doors, the roof. The building envelope plays a massive role in maintaining the climate in a facility. Steam, which is typically generated using a boiler, is used in various industrial processes from heating to power generation. So these systems, along with equipment specific to their processes, represent all or most of the energy used in a typical industrial facility. Each of these systems significantly influences the overall energy efficiency and energy costs of a facility. So today we'll focus mainly on boilers, but since boilers and steam are generally so entwined, we'll also touch on steam as well. So we'll begin by looking at the fundamentals. What is a boiler? What are the main components of a boiler system? These things are key to understanding how boilers operate and how their efficiency can be improved. So boilers, simply put, a boiler is a closed vessel that converts fuel to heat. That's the goal of a boiler, convert fuel into heat. In reality, it's a lot more complicated than that. Boilers come in many varieties, depending mostly on the fuel and the application, as well as the capacity. Boilers can be designed to accept a wide variety of fuels, including natural gas, propane, biogas, coal, oils like diesel fuel, biomass, and electricity. The heat that's generated by the boiler can serve a multitude of purposes. A boiler can be used to heat water, to supply hot water or steam to the facility. A boiler can be used to heat up heat transfer fluids like propylene glycol or ethylene glycol for things like snowmelt systems, freeze protections, process heat, various other uses. A boiler can be used to heat the air for facility heating, process heating, and other heating purposes as well. So the overall design of the boiler would depend on these factors and others. So boilers can be very different from one another. However, they generally have several similar key components. So at the core of the boiler is the combustion chamber. That's where the fuel is burned. On gas-fired and oil-fired boilers, you'll also find burners that deliver the fuel into the combustion chamber. The burners control how much fuel enters and helps manage the air-fuel mixture to ensure total combustion. The heat that is generated then moves through a heat exchanger where water is heated to either hot water or steam, or a heat transfer fluid is heated. The flue gas system carries away the exhaust heat, and a control system, especially in more modern units, keep the boiler running safely and efficiently. So there will be some differences depending on the type of boiler. For instance, I mentioned electric boilers. They're not going to have a combustion chamber. They're not going to have burners. A biomass boiler, another type that I mentioned, doesn't need burners because it's using solid fuel. Each part, however, plays a critical role in making sure the boiler does its job smoothly and sustainably. So now that we understand the basics of boiler systems and how they work, let's get into the different types of boilers. As mentioned earlier, boilers aren't a one-size-fits-all. They come in various designs depending on the application, the fuel source, the capacity. So let's look at some of the ways that boilers can be classified and the applications of each type. So boilers can be classified by the type of fuel they accept, by the internal design, by their application, and also by how the air is moved through the boiler. There may be other classification methods, but these are four of the main design considerations. So fuel type is probably the main contributor to how a boiler is designed. Gas-fired boilers are boilers that use natural gas, propane, biogas, hydrogen, or other flammable gases. There will be minor design differences based on the type of gas that the boiler accepts, but generally, these boilers can be similar. In most cases, these boilers can be easily converted to use a different type of gas as a fuel. These are the most common type of boiler that we'll see, since natural gas is readily available and relatively affordable throughout most of the US. Oil-fired boilers will use oil-based fuels like diesel fuel, kerosene, fuel oil, biodiesel, or others. These boilers require the fuel to be delivered by truck and therefore are not as common in industry. These boilers are more common in areas where natural gas is not readily available. So next is coal-fired boilers. Those are boilers that burn coal. They're generally on the decline, but they do still have their place in industry in some areas. In most situations, the coal must be trucked in. And additionally, these boilers must be equipped with emission control devices, especially in areas with strict emission controls, and that can drastically increase the cost of the system. Biomass boilers are those that rely on the combustion of organic material, biomass, to generate the heat. Biomass can include materials such as industrial and municipal waste, crop residue, algae and seaweed, wood products like logs, bark, wood chips, and sawdust, and so forth. These boilers, they're not incredibly common, and they fit best when the facility generates significant amounts of an organic waste. And in these cases, it can be a huge win because with the biomass boiler, they can essentially turn their waste into energy. And if they have enough of it, they could essentially power the whole facility. Electric boilers are significantly different from the others because there's no combustion. Electricity is used to generate the heat, meaning that these boilers have no direct emissions. An electric hot water heater in a home is a very basic example of an electronic boiler. In industrial applications, these type of boilers aren't as common as electricity is typically more expensive per BTU than natural gas and other fuels. Now, with most boilers, if you'd open the outer vessel, the outer shell of the boiler, you'd find a series of tubes in one of a couple different orientations. And the boilers are generally classified by what is inside these tubes. The differences between these two are kind of best depicted visually. So let's look at a couple images here. So the image on the left represents a fire tube boiler. In these boilers, the tubes carry the heat that are generated by the combustion of the fuel. And these tubes pass through the water-filled vessel, and when they do, the heat transfers into the water. And this type you'll most often see being used for facility heating or for small industrial processes. Now contrast that to the image on the right, which is a water tube boiler. In this case, instead of the tubes carrying the heat, the tubes are carrying water through the hot furnace environment, where the heat is transferred into the water. These boilers are more complex and generate higher pressures, so they're better for large industrial applications and power plants. And there are also hybrid designs that utilize both of these concepts. I don't have an example of one of those here. Boilers can also be classified by their application, and their designs will vary depending on the application. So different applications are going to require controlling the heat that's generated differently. So hot water boilers are used to supply hot water to a facility or for use in restrooms, kitchens, hand washing areas, or industrial processes that require hot water. Steam boilers also rely on heating water, but it's heated to the boiling point or higher to generate pressurized steam. And steam can serve a huge array of purposes in industry, from heating, drying, sterilization. It can also be used to generate electricity. And these are just some of the uses for steam. Thermal oil boilers, on the other hand, are used to heat thermal oil, which can be used to transport usable heat where it's needed in the facility. So thermal oil, like steam, has a variety of applications. However, thermal oil operates at low pressure, which makes it can make it different from steam. And the thermal oil can handle higher temperatures than steam. It also won't freeze, and it's not corrosive. So this gives them advantage over steam in some applications. However, the objective of these are all the same: is transporting heat to where it's needed. And finally, the air movement. So for combustion of fuel to continue, there has to be a supply of air. And the boilers can be classified by the way that the air is supplied. Natural draft boilers, they rely on chimney height and temperature differences to move air through the boiler system. However, since the air is not controlled, the air fuel ratio of the boiler can't be controlled, which will have an impact on efficiency and generally a significant impact. This type of boiler we don't see installed anymore. Um, you'll find them occasionally with older installations and usually only smaller scale. The other three types rely on fans to move air through the boiler system. Forced draft boilers use a fan at the air inlet, moving air into the combustion chamber. By controlling the blower fan speed, the amount of air moving into the combustion chamber can be controlled, allowing the air fuel ratio to be controlled and energy efficiency to be improved. Due to the energy efficiency, you'll commonly find boilers of this design in all but maybe the largest industrial facilities. Induced draft boilers, instead of having a fan at the inlet, they use a fan at the furnace outlet to pull air into the combustion chamber and push out the exhausting air. So while the control of airflow into the combustion chamber isn't quite as well controlled, this type of boiler helps ensure that the exhaust gases are all sent out of the facility, and that's going to prevent flue gas leakage in the boiler room. And this type of boiler is most common in large industrial facilities. And finally, there's balanced draft boilers that have a fan at both the air inlet and the furnace outlet. And this design helps maintain stable furnace pressure. And it's going to be most common at large utility scale power plants where the pressure stability is much more critical. So throughout the rest of this presentation, we're mostly going to focus on natural gas boilers and the steam system related with them. That's the most common boiler and the most common application. So just keep in mind moving forward that the information, the recommendations, the best practices, so forth, they may not apply 100% if we're talking about other types of boilers. So now that we've discussed the basics of boiler systems, let's take a deeper dive into efficiency and boiler efficiency. So efficiency, represented here by the Greek eta, is simply the proportion of energy input that is successfully turned into useful output. So let's take a simple, large natural gas boiler for a steam system, for example. Let's assume it has an input of 1 million BTU per hour. That means that it is going to use 1 million BTU worth of natural gas. And that's, since we usually pay for natural gas based on MCF, that's right around 1 CF. 1 MMBTU to 1 MCF is pretty close to a 1-to-1 ratio. So if our boiler is 80% efficient, that means that we should be getting 800,000 BTU of energy out of that 1 million BTU worth of natural gas that was sent into the boiler. And that 80%, that means that it should be transferred into the steam, in this case, as useful. So the remainder of the energy, in this case, the other 20%, is going to be lost. And those losses can occur for various reasons, including thermal losses from the surface of the boiler, incomplete combustion of the fuel. We'll discuss sources of loss in more depth right here. So where do these losses occur? So the largest loss in the boiler is heat lost in flue gases. So as hot gases carry unused heat away through the exhaust, this usually represents about a loss of about 20% of the energy input. So our loss out the flue, the heat that's coming out of the stack, that represents most of our losses. There's also going to be some loss, about 1 to 4%, due to radiation and convection from the boiler's external surface, leading to heat dissipation into the surrounding environment. So not only are we losing the useful heat out of the boiler surface through radiation and convection, we're also heating up the environment, which in the winter could be beneficial, but in the summer, that's more heat that we have to offset or that we have to consider. And the final source of loss will be due to blowdown, which is up to 3%. So water blowdown releases hot water to manage impurities, and that results in this minor heat loss of about 1 to 3%. So these values here are normal for a typical boiler, resulting in a boiler efficiency of about 70 to 80%. We'll see some higher than that, but not too far generally. So that means that we're losing about 20 to 30% of our energy. And to me, as a certified energy manager, when I look at these things, when I see heat being lost, I see dollar bills floating away, because that's literally what's happening. Is we're in any wasted heat is just wasted money. So that's in context of the boiler system. Now, the overall system, if we have, say, a steam system, we can expect some additional losses there, depending on the spread of the length of the pipe that we have, whether it's insulated or not, and how well, and so forth. And that can be another 5 to 15%. So ultimately, when we get to the end use load of steam, we may be only running at about 55% efficiency. So how do we determine boiler efficiency? There are several approaches that we can take, and they generally represent a trade-off between complexity and accuracy. So we can use product specifications. We can use software applications. We can calculate the losses and sum them up, or we can take direct measurements. So let's discuss each of these in a little more detail. So the easiest method of estimating the efficiency of a boiler is to look at the product specification or the equipment labels. The input and output in BTU per hour are provided on these labels, allowing the efficiency to be easily calculated. So I took from one of the assessments that I was on, I took it, put a label up here from the boiler that they have. And from this, you can see 252,000 BTU output per hour, 300,000 BTU input per hour, and that gives us an efficiency of about 84%. So the nice thing about the product specification method is that there's just a simple calculation with no tools required. The thing to keep in mind, though, is that this is the rating from the factory when the equipment was new and operated under ideal conditions. So this doesn't consider aging and wear and tear to the system. It doesn't consider that maybe the burners aren't, or we don't have the proper air to fuel ratio, or maybe something was installed just slightly correctly, or we just never know. These are just under ideal conditions. And this level of accuracy may be fine for some purposes, but there's often a need for more accurate estimates of the efficiency. And also, a lot of times when we're looking, especially if we're looking at old boilers and old facilities, the manual, there may not be an equipment label on it if it's too old, or the label may have been removed or worn out. and this isn't uncommon. So, when you run into this situation, it's really difficult to really figure out anything about the boiler, especially the efficiency. So on the other hand, there are also software applications such as that can help us determine the efficiency of the boiler. The U.S. Department of Energy has a free software called Measure, which is designed to help industrial facilities manage their energy use and improve their energy efficiency. And one tool within this software is a stack loss calculator tool. And this tool will calculate the stack loss, which, if you recall from a few slides ago, is really the primary source of loss in a boiler. This is going to provide a more accurate efficiency measurement than the equipment label will provide, because it's going to take into consideration some of the kind of the setup in the environment that the system's running in and condition that it's running in. The software, though, is a little more complicated. We have to have the stack gas temperature, we have to have the ambient air temperature, and we either need to know the excess air or the oxygen in the flue gas. And those will have to be measured directly. You're going to have a hard time, kind of trying to estimate those. So the best way to measure those parameters, though, is with a combustion analyzer. And the probe that you see on the combustion analyzer is placed in the airstream and the exhaust stack. And the stack temperature, the oxygen in the flue gas, and various other properties will be measured and displayed. These numbers can then be plugged into the stack loss calculator to get an accurate estimate of the stack loss. So while this method provides more accuracy, there is also a cost involved. An entry-level combustion analyzer that will provide the needed measurements is going to cost you $500 or more. If you're in a situation where you need calibration certificates, higher accuracy, that cost of equipment is just going to go up and up and up. Some of these high accuracy, well-featured units from popular, well-renowned brands will cost you upwards of $5,000. And additionally, with this method, we're not considering the losses due to radiation and convection from the boiler or the blowdown losses. And that could present another 2 to 7% efficiency loss that isn't being considered here. So, if that's not accurate enough, we can take it a step farther and we can include the other losses. So we can use the combustion analyzer to determine the stack loss, and then that's going to leave the surface loss, blowdown loss, and when applicable, blowdown ash loss. So blowdown loss can be determined by measuring the temperature of the blowdown water and the temperature of the feed water, as well as the volume of blowdown water release over a measured period of time. So basically, we need to figure out how much heat we put that's still remaining in that water that's coming out during the blowdown. Surface loss can be estimated based on this surface temperature and the surface area of the boiler. And again, the surface temperature, not too difficult. The surface area, that can take a little more thought because of the shapes of some of these. And bottom ash loss, that's only going to be an issue when we're burning coal or other organic material. But quantifying the loss requires determination of the amount of bottom ash, the carbon content of the bottom ash, and the temperature of it. That's beyond the scope of this presentation. So, and we're talking about a natural gas boiler. This isn't an issue anyway. So in addition to the combustion analyzer to do this calculation of losses, we'll also require tools like an infrared thermometer gun to measure surface area, or not surface area, surface temperature, I apologize. And thermocouple or thermometers are similar to measure the water temperature. And again, the surface area of the boiler would also need to be measured or estimated. These additional tools, they're relatively inexpensive and are not difficult to use, but the calculations that are associated with this to accurately estimate these losses are a little more complex. There's a lot more involved to gain that improved level of accuracy. And finally, the most accurate but the most complex method is direct measurement of the input and the output. So to measure the input, we need to know how much energy is contained in the fuel that the boiler uses. So the amount of fuel used per hour and the gross calorific value, which is how much energy the fuel contains per volume, has to be known. The gross calorific value is easy to find. It's published and it's not hidden information or hard to find. But accurately measuring the quantity of fuel used can be a challenge. So how do you measure how much fuel is being sent in through a natural gas burner? We have kind of an estimate from the estimated input, but that's going to depend on the actual number is going to depend on amount is going to depend a lot on the specific boiler that we're dealing with. And to measure the output, we would need to calculate how much steam is generated and how much that steam heat that steam gained from when it was fed into the boiler as water. So we need to know the amount of heat in the feed water and the amount of heat contained in the steam. And from that plus the amount of steam that's generated, we can figure out the input or the output, sorry. So again, this is a more accurate but a more complex method. It's going to require some more sophisticated equipment and measurement. We're going to need flow meters to measure the flow of gas, the steam. We're going to need thermometers to measure temperatures. And then we're going to have to kind of put that all together and get our input and output and calculate our efficiency. So this isn't something that we would normally do during an energy assessment unless it was unless there was a very specific reason that we needed this level of accuracy. So now that we've identified where efficiency losses occur, and we've discussed some factors influencing the efficiency, let's begin exploring how we can improve the efficiency of the system. So again, these following recommendations, they aim to improve boiler efficiency, lower energy costs, and reduce emissions. So we'll walk through actionable strategies designed to address the losses we've seen and help make the boiler system as sustainable and cost-effective as possible. So first, we want to make sure that the air-to-fuel ratio is optimized. So this is one of the most critical steps in improving boiler efficiency. Getting the air-to-fuel ratio right is essential, as too much air will result in excess heat being lost up the stack, and too little air causes incomplete combustion, which creates soot buildup and harmful emissions. And both of these not only waste energy, but also drive up operating costs. So by fine-tuning this ratio, we can ensure cleaner, more complete combustion, better heat transfer, and improved fuel savings. It's a relatively simple adjustment, but it can have a major impact on performance and cost. So for most accurate results, it's highly recommended to use a continuous flue gas analyzer that provides real-time feedback, but periodic testing with a combustion analyzer is a less expensive option. So The measurements from a combustion analyzer, along with software like Measure, can be used to determine the air to fuel ratio and calculate potential energy and cost savings for making adjustments to the boiler. So after measuring the ambient temperature, combustion air temperature, stack temperature, excess air, and emissions using the combustion analyzer, Measure's flue gas loss tool can be used to determine the amount of excess air. So by inputting the data collected from the combustion analyzer into the software, along with some other basic information, including fuel cost and operating hours, the software can estimate the losses in flue gas and the excess air. A modified scenario can then be generated where updated values can be input to see how those outcomes change. When the air to fuel ratio is adjusted, the goal should be reducing the excess air level as low as possible while avoiding an increase in boiler emissions reported by the combustion analyzer. So an increase in emissions means that the fuel is not combusting completely due to insufficient air. So if we find that point where the excess air is as low as we can get it and the emissions are under control, then we found kind of the optimal position. So if you look at the example above, the results show how reducing the excess air in the scenario from 15% to 18% or down to 8% would impact the efficiency. So we can see the amount of flue gas losses and compare them. Okay, sorry about that. And then we can look at, based on the details provided, the software can also estimate fuel use savings and corresponding cost savings due to the modifications. Next, we'll discuss using economizers to improve efficiency. So exhaust stack gases contain a lot of unused heat. Exhaust stack temperatures exceeding 350 Fahrenheit are not uncommon. And the money to generate that heat, it's already been spent. So instead of just sending that heat out of the exhaust stack, an economizer, including a condensing heat exchanger, can be installed to recover a large portion of that heat. So a condensing heat exchanger can capture both sensible heat, which is related to a change in temperature, and the latent heat, which is the heat released during the phase change from steam to water. This recovered heat can be used to preheat the water going into the boiler, cutting down the energy needed for steam generation and improving overall efficiency. So if we consider a boiler that has an input of 1 MMBTU per hour, we can expect about 15% of that energy to be lost through the stack without an economizer. If we can capture just 20% of the exhaust stack heat, we can save 30,000 BTU per hour. If that boiler runs 24 hours a day, 7 days a week, and it was using natural gas at $8 per MMBTU, you're looking at savings of nearly 263 MMBTU, or over around $2,400, between $2,000 and $2,500 a year in savings. And the implementation, based on the implementation cost of an economizer for this size boiler, which is around $5,000 to $7,500, we're looking at a payback period of 2 to 4 years. So next, we'll discuss the replacement of old burners with new, more efficient burners. Old burners are often inefficient and inaccurate in how they mix the fuel and the air. Over time, this leads to incomplete combustion, higher emissions, and wasted energy. Replacing them with modern, high-efficiency burners can significantly improve boiler performance. The table here shows the findings of a case study at a facility with a large 50,000 pound per hour process boiler. The boiler was found to use about 500,000 MMBTU of natural gas per year, costing around $4 million. So they're spending about $4 million a year on natural gas. By replacing the old burners with a burner that improved efficiency by just 2%, a savings of over 12,000 MMBTU and nearly $100,000 per year could be realized. At an installation cost of about $75,000, the simple payback period of this is less than 1 year. So, compared to $4 million, 100,000 isn't a huge amount, but it's definitely a notable amount, especially if that's something that we can gain with this installation that'll pay for itself within a year. So the next recommendation is to insulate hot surfaces and boiler pipes. So according to the U.S. Department of Energy, proper insulation can reduce the losses in the distribution system by up to 90%. So, and they recommend that any surface above 120 degrees Fahrenheit, including boiler surfaces, piping, fittings, any of them over 120 degrees Fahrenheit should be insulated. It's one of the simplest and one of the most effective energy efficiency upgrades available to a boiler and steam boiler system and steam system. So any hot surface that we leave uninsulated is just another opportunity for the excess heat to escape, which again is just throwing money out the window. So you can see from the table that even uninsulated low pressure steam lines can have a significant waste. So for instance, if we look at the chart, 100 foot of uninsulated 2-inch steam line can result in a loss of 235 MMBTU per year. If we're paying $10 per MMBTU, that's $2,350. And 100 foot of insulation for 2-inch steam line, $250 or less. So again, that's a situation where payback period is just a month or two. Some of the common insulation materials for steam pipes and boilers are showing here. Calcium silicate is the most widely used due to its durability and thermal performance, but there are other options like fiberglass, polyurethane, polystyrene, mineral wool, polyisocyanurate, and so forth. So the choice of material depends on factors like surface temperature, exposure conditions, and the cost. And the goal here is to minimize heat loss and keep the system efficient while ensuring that the insulation holds up over time. In a lot of cases, when you find uninsulated steam pipes, at some point in their life, they were insulated. It's just failed and fallen off and removed and never been replaced. So next, one often forgotten part of a steam system that can affect efficiency, if not properly maintained, is steam traps. Steam traps play a key role in an efficient steam system operation. Here you can see a schematic of a typical steam system with traps located throughout to remove condensate from without losing valuable steam. To keep these systems running efficiently, it's important to regularly inspect traps for leaks or malfunction. One simple check is to compare the temperature at the trap's inlet and outlet, and if they're the same, it may not be working properly. Worn or clogged traps should be cleaned or replaced as needed, and using a dedicated steam trap testing tool can help identify issues early on. Maintaining steam traps ensures that steam is used effectively for heating or process needs rather than being wasted, saving both energy and cost. So next we'll look at steam leaks. So what you see here are examples of typical steam leaks, often found around joints, valves, flanges, or corroded sections of pipe. These might look minor, but they can waste a significant amount of energy and water over time, and even a small leak results in a significant loss of steam annually. While steam leaks are often visible and audible, some may not be immediately apparent. The pipes may be close to the ceiling or otherwise not easily visible or accessible, and a noisy environment may mask the sound, especially with smaller leaks and especially in loud environments. So we can use an ultrasonic leak detector to help locate these leaks by detecting the ultrasonic noise associated with pressurized leaks. And they're very simple to use, and they're affordable. And once leaks are detected, repairing them is pretty straightforward. And finally, we'll discuss overall boiler system maintenance. So proper boiler maintenance is critical to ensure continuous, reliable, and efficient operation of boilers. The core elements of a sound maintenance routine include the following. First, having a dedicated operator ensures accountability and consistent monitoring. Daily tasks like manual blowdown and water sampling help control scale and corrosion. Periodic checks of burner heads and orifices maintain combustion efficiency. Using automatic blowdown systems for the top helps reduce manual labor while maintaining water quality. Chemical dosing must be monitored monthly to protect the boiler from internal damage. And importantly, scheduling 2 to 3 planned shutdowns annually for in-depth inspection and cleaning ensures system reliability. And finally, modulating controls can help keep steam pressure steady and reduce energy waste. So all these steps together form the foundation for a safe, efficient, and long-lasting boiler performance. So with that, here are the references for the presentation. And I'd like to thank you for joining today. I'll take some questions in a moment, but before we do that, remember that if you have any questions after the presentation related to what we've discussed here or pollution prevention in general, please feel free to reach out to me or Dr. Ashish Nambarte, and we'll do our best to answer any questions you may have.